Okay. So I haven't banned the use of it or anything like that, but I don't think it's particularly useful to rely on it, given that you're going to have to demonstrate skill at the end of the course, right? So, yeah, I think it's helpful too when I have a question that I can't resolve any other way. Which happens a lot. I think I mentioned it earlier, though, that LLMs probably have 100, if not 1,000-fold more examples of software code to train on than they do hardware related code. And so their accuracy with hardware is probably a lot more limited, and it's an area where there's so many other things you've got to think about that you often need to vet what you get provided to you by an LLM as a hardware description code output, right? So just be aware that there are many possible errors that are occurring, and they can be very slight. We got quite a few coming up in, I think it was Lab 4, Lab 4 marking. It was apparent that some people were using LLMs, and it seems like one of the issues that the LLMs were throwing up were they were providing an active low asynchronous clear for one component and an active high asynchronous clear for another component in the design. And obviously that's inconsistent in terms of the design process. So if you were trying to maintain that code, you'd be expecting to see, they're using active low clear, so that's going to be the case all the way through the design, and that's what you would expect. But for some reason or other, these LLMs were sort of generating code that on the one hand was active low and on the other active high. So it sort of raised this issue in our minds a little as to what the best approach is. So I'm just mentioning that I think it's fine to use it to try and learn, but be careful in your usage and try and vet as closely as you can what is being produced. If you're relying on something that it's produced, you should be understanding what it's produced at the very least. Okay, and remember that during the final exam, you won't have access to an LLM. Are there any questions on that? All right, does it make sense that you shouldn't have mix active high and active low resets within the one design? It sort of seems a bit silly. On retrospect, when I reread over the spec, I didn't specify whether it should be active high or active low. And that's a failing on my behalf. But it didn't seem like we got any questions from students either before submission date. Should this be active high or should it be active low? So in future, I will change the spec so that it's spelled out a little bit more clearly. All right, so where are we right now and what are we still looking at doing within this lecture on digital systems design? We've looked at a number of designed problems so far and followed a formula for developing a solution to those designs, where we first figure out, well, how are we going to perform this computation? So what algorithm are we going to be using? Then determining what data, I guess what data path components are needed to implement that algorithm, and of course concerning ourselves with the control of those components so that we are putting that algorithm into effect. Effectively, all of what we're doing is hardening algorithms. We're trying to show how algorithms that you're familiar with from the software scene can actually be implemented in hardware as a laid out spatial structure that, given data, will just compute what you want it to compute in a deterministic number of clock cycles. So it's quite different usually from what's done in software, where of course the performance is dependent on so many other things as well, interrupts coming along, and perhaps interrupting for thousands, if not millions of cycles, all sorts of other things coming along. Of course, software usually being inherently sequential, whereas in hardware we can be as parallel as we would like to be, limited only by what we could put on a chip. So today we're going to look at two different algorithms for performing binary division, and we're going to look at a final algorithm that makes use of this design to see how you encapsulate one design in another. Okay, so the first example is to look at binary division. So just to remind you of the school book division approach that you've taken in your normal decimal division. If you're not using a calculator, you have to figure out, what are the leading digits, what are the most significant digits of our dividend that we need to use in order to be able to subtract some multiple of the divisor from recording that number up here, as in 1 lot of 9 subtracts from 14, it doesn't subtract from 1. Pulling down a remaining digit and then determining again whether we can, keeping on pulling down remaining digits until we can subtract some multiple of the divisor once again. In this case, 5 lots of 9 from 50 to leave a remainder of 5 and a quotient of 15. So how do we do this in binary? Well, in binary it's done exactly the same way, pretty much. So this calculation here is exactly the same as this calculation. So you'll see how that works. But obviously now, what we need to do is scan the most significant bits of the dividend until we have enough bits available to be able to subtract the divisor from that number of bits. And of course, we're only ever going to be able to subtract either 0 or 1 lots of the divisor away from some number of bits. So we'll never see anything but a binary quotient coming out here, right? So in this case, it's not until we've considered the leading 5 bits here that we can subtract 9 away from it. And of course, that's 17 less 9 leaves 8. So that's the remainder that we have. And then we can move on to the next bit position, pulling that guy down, and it just so happens that again we can deduct 9 from that, and so on for each remaining bit. And every time we can, of course, deduct a copy of the divisor from some partial dividend, we add another 1 to the less significant end of the quotient there, until finally there are no bits left. And then we're left with a remainder here, which in this case happens to be the same as what we have up here. So clearly 15 and 5 as the remainder is what we would have expected, given they were the same calculations that we were performing. So this raises the usual questions. So how do we perform this computation? What data path components do we need? And how are we going to control them ultimately in our hardware design? So I'm going to put up the pseudocode up here for this computation that we've just performed, the binary version of division. Since we're always considering, some subset of the leading bits of this dividend, we're going to use a shift register R that we're going to shift the bits of our dividend A into. So from the most significant bit end, they're going to be added into R. And we're going to do our determination of whether we can subtract the divisor B from R, right? That way we keep control over how far we've progressed with shifting the bits across and what the remaining bits are of A that haven't yet been considered. And we basically know that as soon as R is larger than the divisor, we can subtract some, larger than or equal to the divisor, we can subtract some copy, a copy of the divisor away. So when R is greater than or equal to the divisor B, then we can do the subtraction, update the remainder that's in here, and add a 1 into the quotient. So this is the n minus 1 minus ith bit of the quotient has to get an I in there, has to get a 1 in there. Otherwise, if R is less than B, well then we can't subtract B away from R, and therefore we shift in a 0 into that bit position of the quotient. So that's what happened here in these leading bit positions up here. Is that all good? Any questions on this so far? Okay. In that case, let's have a look at then how we're going to control this, bearing in mind that there's a few things that we know we need. We need these shift registers for A and R. We'll need some sort of counter in order to be able to know that we've counted down the right number of bits. And we need a quotient shift register as well. So we haven't really quantified that precisely. We're just going up with a high-level ASM chart to start with. So in terms of our pseudocode that we have here, initially all we're doing is clearing the register R. And in that period while we're doing that, the user can be loading A and B until they've done that and then can assert some start signal. So 0 being loaded into R and n minus 1 being loaded into the counter are really just the initialization of this entire process. And then states 2 and 3 really cover the for loop that we have here. The way the ASM chart is being constructed, first we shift A into R, or the first bit of A into R. Always the most significant bit that's remaining of A gets shifted into the least significant bit of the R register. And then we perform this check of whether we can deduct B from R. And of course, if we can't, we shift 0 into Q, but if we can, we're going to shift 1 into Q, and we're going to perform that subtraction and update R, right? And finally, we can check whether or not we've finished with the for loop, which will occur when the count has become 0. And when the count does become 0, then we can assert a done flag to indicate to the user that we're finished with the division. All right? So there's a number of other questions that this raises. One that you might want to think about is, how will we know that R is greater than or equal to B? So if we're doing some sort of binary calculation, how do we know that R is greater than or equal to B? How would you go about figuring it out? What if R were 1 and B were 2? How do you do this comparison? How do we normally do a comparison? Here's R and here's B. How do I know R is greater than B? Come on. This is not second class. This is second year. How do I know that R is greater than B? Yes?
Maybe like subtract R with B.
Subtract B from R is what I'd like to hear, and determine whether there's anything left over, right?
Maybe it's like 0 or like something like that.
Yeah. So how do we know in a binary number system whether R is greater than or equal to B? Let's say R is 1 and B is 2. Is R greater than B? How do I know that? Yeah, if I subtract B from R, I have to add the 2's complement, right? Okay. What if R is equal to B? Well, then I'm going to have 0, 1, 0 and 0, 1, 1, right? I'm going to have a 1 carried in here and a 1 carried out. And if R is 2 and B is 1, then we're going to have 1, 1, 1, 1, 0, 0, and again, a carry out of 1, right? Up here, when R was smaller than B, we had a carry out of 0. When R was equal to B, we had a carry out of 1. When R is greater than B, we had a carry out of 1. So the carry out tells us whether R is greater than or equal to B. Okay. The pseudocode counts up from 0 to n minus 1. Why are we counting down to 0? No. No. Not really. No. It's got to do with perhaps ease of use in the code and maintainability of the code. What if what if n changes? Then I'm going to have to be checking for a different value every time down here. How am I going to do that check? Then I'd have to change whatever comparator I'm using there. Whereas the comparison with 0 is straightforward, right? We know how to do that. We just gnaw all the bits together. So it makes life easier if we compare with 0 than if we compare with n minus 1. What's the value of count inside state 4? So when we've reached state 4? Fallen into my trap. Who said 0? Aiden. Fallen into my trap. How do we know it's not going to be 0? If it's 0 here, how can it be 0 when I get into S4? Sorry? Yes, it'll be -1 or effectively -1. It'll be a wraparound, I guess, on whatever the value of the counter is. Why? Because we've set this more action in state 3. So every time we get an active clock edge in state 3, even the one that takes us into state 4, we're going to be subtracting 1 from count, right? So be careful. Right? Okay, so let's have a look at how the data path can be constructed for this. So we need a register, a left shift register for the dividend A. We've got our B register, which is the divisor. We've got to shift the most significant bit of this shift register into another shift register R, and we want to be able to update this shift register R with the difference between the current value of R and B whenever the carry out is 1. Right? And irrespective of whether the carry out is 1 or 0, we're going to be shifting that into the Q register, the quotient register, on every clock cycle. Okay? We're subtracting B, hence complementing all the bits and adding a 1 in, so that's our 2's complement. Right. So that shows us all of the control signals that we have here, EB, LA, LR, ER, EQ, and R cell. And it also shows us the status signals that we need. Carry out is a status signal. That tells us whether we need to load a new value into this shift register or not. Right? When carry out is 1, we want to assert LR, not ER. Yeah. What else do we? Well, we want to know also when the count is 0. Where's the count? Well, it's up here. So we've got to initially load this counter with n-1, count down on every internal clock cycle within the for loop, and when it's 0, that tells us that the shifting has stopped. Right. Any questions on this? So on the data path that we've illustrated here. So given that we now have the data path and we can see the control signals, and I'm expecting you to be able to do this, clearly label all of the control signals, all of the signal names, A, B, R should have a name, doesn't have a name, that's bad. Yeah, it does have a name here, R. Q, etc. We know the sizes of each of those as well. So now that we have the original ASM, the high-level ASM with the pseudocode, and we have our data path, we can refine the ASM chart so much so that, you know, what does it mean to clear R and to set the counter to n-1? Well, to clear R, what do we need to do? We need to set R cell to 0 and assert LR, right? And to set the counter to n-1, we have to load the counter, assuming it's being loaded with the right value. So that's what we see up here. And we do that until S is asserted. The load A and load B, they've disappeared. Why? Why have they disappeared? It's not a trick question. It's what we've been doing all along. But you've got to stay alert to what you're doing here in terms of changing the ASM chart. Remember, it's the user that's going to be loading A and B. That comes from outside the circuit. So there the user has to assert LA and EB. So when the start signal is given by the user, then what do? Well, then we start our shifting. This said shift left R in parallel with A. Well, that means EA and ER have to be asserted, right? And it's the most significant bit of A that gets shifted into the R register. And then in this second cycle here, we're counting down, so that means asserting the EC signal, right, as we see here. But we're also, which isn't really sort of explicitly mentioned here, other than shifting 0 into Q and shifting 1 into Q, since we're always going to be shifting something into Q, asserting the EQ signal up here, and having cleared the R register initially, the only thing we'll ever do in terms of loading the register is loading it with the difference between R and B. So R cell is set to 1 within this state, all right? So we're always going to be loading this register. When we do load it, which only happens when the carry out bit is 1, then we want to get the data that's coming through the left-hand path of this mux, right? When the count is 0, then we're going to enter state 4, right? But on entering state 4, we still have EQ active, R cell equal to 1, EC active, and potentially even LR active. So all of that might still happen on that final shift, on that final, clock edge that takes us into state 4. And that's it. We stay in state 4 until the user deasserts the start signal, has read the quotient and the remainder, and then we can return back to state 1. Any questions about this? Okay. So note here that the inner loop, the for loop, takes up 2 clock cycles. That's perhaps a little less than desirable. Ideally, we should only be expending 1 clock cycle per bit in the divider. So that happens because we've got to, on the one hand, shift the R and A registers to the left, and on the other hand, we want to update that R register with the difference between R and B when it's necessary. So we always have to shift into the R register, and sometimes we want to then do a subsequent reload of that R register, right? So that's what's happening over here. We're always shifting in, but then based on whether or not the carry out is 1, we want to reload that register. So it's suggested here how we might overcome this, and it's a little bit tricky, but it's very effective. So the idea is that we're going to have one extra flip-flop apart from the R register, and we're going to shift into the R register from the A register via this one flip-flop. So it's like a spare flip-flop. When we do our determination of whether R minus B is positive, 0 or positive, we take into account the least significant n minus 1 bits of R and that extra flip-flop. So that's the bits that we'll be using. But when we update R, we only update the n bits of the R register. We don't update that least significant bit, the flip-flop. So here's our R register, and here's this extra flip-flop. So the way it's going to work is we're going to use the least significant n minus 1 bits of R plus this flip-flop as the new R value. And we're going to do our determination of whether we can subtract B away from it. And if we can, we're just going to update the R register at the same time as reading the next bit from our A word into that flip-flop, and thereby achieve both the shift into the R plus the update of R in one clock cycle. Okay, so this is a little bit tricky. But I hope it's clear what's going on. Add a simulation of it in a moment. Are there any questions about this at the moment? Then I will move on. So far we've been using a second register Q to store the bits of the quotient. But since we're shifting the bits of A out, we could reuse that register and thereby save us that n-bit shift register. So we're going to use the vacated bits of A to store the quotient Q. All right, so let's have a look at how this works. So this is the same calculation simulated with these enhancements. All right? So initially we load, this is our initial state, and then we perform one shift before we start. So this is our first shift. Here's our spare flip-flop, RR0. So it's playing the role of the least significant bit of R when we determine whether or not B can be subtracted or not. So we see the most significant bit of A, this is our original A, is shifted into this flip-flop. So for the sake of checking whether R is bigger than B or not, in that cycle labeled 0, the value we're comparing with is 1. All right? All of these zeros and 1. So obviously we can't subtract 9 from 1. In the next clock cycle, so that first determination of whether we can subtract B from R or not, that leads to a negative C out as a 0. So that gets shifted in at the same time as we shift the next 0 into RR0, right? So as we shift this guy across, we're shifting the 0 in. That's our quotient bit from that very first cycle. So as the RR0 bit gets shifted into the R register, we now have 2 in the R register effectively that we're comparing with. That's still smaller than Q, than B, so we shift another 0 in. As we shift the next 0 into RR0, now we have effectively 4. That's still smaller than 9, so no go. Then we have 8, which is still smaller than 9, so we still have no go. And on the next clock cycle, we have the 8 that's in the R register plus the 1. So that's effectively a 9 now, right? Sorry, not a 9, that's effectively 6. The 8 here is effectively 16 plus 1, 17. So now we can deduct 9 from 17, leaving a remainder of 8, which gets written into R here at the same time as we write the 1 into our quotient and read the next bit into R0. All right? So at this point, we again have 8 in the R register, but that's really 16 because it's shifted over by 1 bit with respect to RR0. So we have 17 as the total value. Again, we can deduct 9, leaving 8, and a second 1 gets shifted in to our quotient register. Since in this next cycle we have 16, minus 9 leaves us with 7 when we update. 7 times 2 is 14, so I've effectively got 14 here, which again we can deduct 9 from, leaving us with 5 in our R register. So the final result is 15 plus a remainder of 5 in the R register. Queries? All good? So through this trick of using an extra flip-flop, and admittedly an overhead of 1 clock cycle of pre-loading this flip-flop, or if you like, a trailing clock cycle where we have to move the last bit, we have to do that last calculation on R, we've converted 2 n clock cycles into n plus 1 clock cycles for performing this division. So that's quite a nice improvement. Right, if there are no questions on this, I'm going to go into the code and then we'll have a look at a simulation. Any questions? All right, so better just have a look at what the enhanced hardware and ASM look like. So the top bit's the same. This is our A and B registers. We have our subtractor here that subtracts the R register contents, or subtracts B from the R register contents and updates the R register. Here's our additional flip-flop, right? And it's being loaded by the A bit that's coming in here. That gets loaded into this flip-flop, which then passes it into the R register. So the contents of the R register here, the n minus 1 least significant bits of the R register are taken, so that's n minus 1 bits are taken from the R register, together with the RR0 register. So here's our n bits loaded into the subtractor. In terms of the impact on the ASM chart, I don't know that there is, instead of having 2 cycles here, we only have 1. The top bit's the same, we still clear R, load the counter, we do our first shift, or when the the start signal is asserted, we get ready to perform the first shift when we enter state 2, all right? And in state 2, we're in the for loop. So this is where we're going to be always reading an minus 1 into this flip-flop, and of course shifting the A register, shifting the R register, and making sure that we're always writing the difference back into the R register when that's called for, namely when the carryout is 1, we're going to reload this R register. In this case, the counter is only counts down while Z is while the counter is non-zero. As soon as it becomes 0, EC is not asserted. So that means our counter is not going to go down any further when we hit the done state. All good? All right, so I'm probably zoning you out already. Okay, the code is a bit lengthy. It's spread over 4 slides. The initial slide only has the entity in it though. So S, L, A, E, B, they're the control signals that the user circuit provides our circuit with. And the data A and data B values, the dividend and the divisor. And R and Q are the remainder and quotient that are read by the user when the done signal is asserted. All right? So R and Q are buffer type signals here, or mode signals. Right. Well, that's going to be a bit hard to read, I imagine. Can you read this okay? Or not? Not really? It's the same code as we've seen many times already. Oh, that's not good. Got to make it 80. Still a bit hard to read, isn't it? It's a bit better. Right, so the state transitions are the same as we've seen in other designs. There's only 3 states here. So we stay in state 1 until the S is asserted, stay in state 2 until Z is true, and then we stay in state 3 while S is asserted. More importantly, let's just have a quick look at what the internal signals are for this design. Apart from the state type, the enumerated state type and the state type variable, we have our control signals, our status signals, 0, C out, Z, and we have the status signals, EA, RCell, well that's a control signal, LR, ER, ER0, all of these are control signals actually, not their control signals, these are status signals. We have our A and B register, our data R register. Note that the sum register is 1 bit larger. It's n down to 0, not n minus 1 down to 0. That's so that we can capture that carry out and examine it, right? And we have our count value, which is an integer in the range from 0 to n minus 1. All right, so it starts off at n minus 1 and counts down. I don't know that there's anything more. Gee, this projector's pretty crap. Right. The FSM outputs tell us what the control signals are based on the status signals and the current state, Y. So S being C out and Z being status signals. Because this is a combinational process, we want to make sure that we don't imply any memory. Therefore, we clear all of the control signals. We give them a default value right at the beginning so that none of them are changed in value so that they're all given a value within this process and none of them have to remember what the value was when we entered this process. So this is literally just a transcription of what we see here in this ASM chart. So when we're in state 1, we want to set LC to 1. RCell is already set to 0, so we don't need to worry about it. And if S is 0, then we set LR to 1. It's not really necessary to set EA and ER0 to 0, but it's done here just for nicety to remind you that that's what values they should have, especially when S is set to 1, we want to set those. EA is set to 1 and ER0 being 1. Remember, these are the values that we need to be able to shift out of our A register and into the flip-flop down here. Right. In state 2, we're asserting all of these signals, and then if Cout is 1, then we want to assert LR, otherwise we don't. And if Z is 0, then EC is going to be set to 1, otherwise EC is going to be set to 0 to make sure we don't count down any further in our counter. And finally, in state 3, we assert the done signal. Are there any questions about this? Okay, then a couple of questions for you guys. When is the first shift of the A and Q register done, according to the ASM chart? When is the first shift done? What signal do we need to assert to shift the A and the Q registers? Well, it is only one register, it's the A register, right? What signal controls that shift? EA, yeah. So where is it asserted first? Above S2 here, yep. So when is the first shift of AQ done? Sorry?
The clock signal coming out of S2.
What do you mean by the clock signal coming out of S2?
From S2 to S3.
No. The first shift, yeah.
Is it done on the first edge after S1 when S is equal to 1? It asserts the A?
Yes, which is the clock cycle that takes us into state 2. Right. Yes, indeed. Given that we're asserting it here conditionally when S is 1, when the active clock edge comes along that takes us into S2, that's when the first shift is going to take place. Right, because EA is asserted. When is the last shift of the AQ register done? I understand it's very detail-oriented to ask these questions, but these are crucial in terms of the correct hardware behavior. If we're off by one clock cycle, the division isn't going to be right. So in this particular case, when is the last shift of the AQ register done? I'll come back to remind you about this in a moment. Sorry?
When the count equals 0, because it goes back on to S2.
That's a very indirect way of explaining it. Can you be more direct?
I mean, obviously, each time you shift, count decreases. So when you're at Z there, as it Z equals 0, it'll go back to S2 once more, and then it'll go to count equals -1, and then go back.
So when is it shifted for the last time? Say again?
On the clock edge that moves it to S3.
Yes, correct. Why were you reluctant to say that, Aidan?
Well, I didn't know that it would shift going to S3.
We've got EA there, right?
Yeah.
What does it mean?
And then shift for
It's a more type action in state 2. And that means that even when we're heading out of this state, on that clock edge, it's going to take effect, right?
Yeah.
Always, irrespective. Whereas EC is not taken on that clock edge that takes us into state 3, because it's not asserted in that case. Z is 1, and so EC isn't asserted, so we don't count down any further. The counter will state 0. All right. Oh, God. Sorry. It's actually green on my slide. I don't know why it's blue there. At least it's green now. Right, here's the data path. I don't think there's anything mysterious about it. Our register B, which is this guy that stores the divisor, it's going to be loaded when the user asserts EB with data B. Our shift register R is down here. It has the input value R0, which is the output of this flip-flop coming into it here. It's loaded when LR is asserted or shifted when ER is asserted. We have the MUX DFF, this guy here is R0. It has 0 as one of the possible inputs and AN-1 when ER0 is set to 1 and the output is R0. We have our A register up the top here, loaded when LA is asserted by the user or shifted when the system asserts EA. We have Q is just assigned whatever A is. We have our down counter, which isn't depicted here, that gets loaded with N-1 when LC is asserted, otherwise counts down when EC is asserted, and Z is assigned 1 when count is 0, otherwise it's 0. Finally, we have our sum here. The sum is the concatenation of R and R0, so it's an N plus 1 bit signal, because R is N bits large and we have a 1 bit value here. And we're adding to that not B plus 1. So sum is an N plus 1 bit value where C out is the most significant bit of that value sum. Finally, data R, which is the input to our R register, is all zeros when R cell is 0, this guy here. Otherwise, it's the least significant N bits of the sum register. All right. We're now in a position to talk about the simulation. Are there any questions about the code at this stage? Okay, it's all a bit dry, I understand. So the simulation looks dense. So LA in data A, EB in data B, and S are all specified by the user. Okay, so they're the stimuli, along with the clock and the reset signal that we have up the top. Then we have the done signal and all of the responses of our system. So at this point here, on the rising clock edge, we have the A and B, the dividend and the divisor being loaded by the user. We see Q going to A6, right, which is the value A on this rising clock edge. And we're still in state 1 at this point in time, but given that the user asserts S on the next rising clock edge, we enter state 2. The other thing that's worth noting here is that the count value gets set to 7, well, on an active clock edge here while we're in the reset state. Yeah, that was a more input. Remember the LC value. it stays at 7 for the first clock cycle that we're in S2, because we're not counting down until that Mealy action of EC is asserted during state 2, and it doesn't happen for the first time until the second clock edge that we're in state S2, or the first one that we're fully within state S2. Now, it's worth noting a few things. Now, again, the colors are completely off. So imagine this is green, because that's the color I've got it at here. I don't think it really matters. Let's just leave it as such. So we enter state 2, and that is the very first clock edge that the first shift occurs, right? So A6, 1010, 0110 becomes 4C, 0100, 1100. So I've shifted it across by 1 bit, right? Moreover, the leading bit of A, the 1 in 1010, is loaded into R0. So that's as we expect, right? So when we have this state, our R register, the nominal R register value is just 1, the bit that's in R0, right? So we take the least significant n-1 bits of R plus this guy together, concatenate them, and that's our new value of R that we try to deduct our value of 8 from. The divisor is 8, right? Can't deduct 8 from 1. So we shift again the 4C. So we currently have 4C in our A register. We're going to shift that guy. So this is going to become 9, 8. That's what we see there. The 0 that I had at the leading edge here, that goes into our R0 register, and the contents of the R0 register get moved into the R register. So here's the 0. In fact, as you read along the R0, we see 1010, 0110, which is what we would have expected, given that it's the bits of A6 that get shifted through R0 here, right? So in this second state, in this second cycle, while we're in state S2, we now have a 1 in register R, but you have to sort of double whatever's in register R, because we've still got this little flip-flop R0 at the side. So this is really 2, 0, whereas previously we had 0, 1 in R, but we've shifted it across by 1 bit position. 2 is still less than 8, so no go. We shift over our 9, 8. We're left with 3, 0, right? Because we take that 1 off. We add another 0. We've got 3, 0 there. We shift that 1 that I just rubbed out into R0, and our R register shifted across by 1 bit. So now effectively we have 4 plus 1, 5 in R, but that's less than 8 still. Then we have a 5 in our R register here, but that's effectively 10. So at this point in time, we actually have a large enough R value to subtract B from. We have 10 in there. And of course, the remainder is going to be 2, which is what gets written into the R register on the next clock edge. At the same time, we will write a 1 into what's left in our A register, which by this stage is C. So we've dropped these 2 zeros. We added another 0, and we've added a 1. So we've got C1 in there now, right? Which is what that is. So we have a few more bits to process. So 2 is effectively 4. That becomes an 8. We can deduct 8 from 8 here, right? Actually, we've got a 1 that was shifted in. They're the 2 1 bits from C that get shifted in here. So we've got 8 plus 1 is 9, so we can deduct 8. That leaves a remainder of 1, which gets updated here. Of course, we can't deduct 8 from 3. We can't deduct 8 from 6. And so there's no more deductions possible. But by this stage, we've done 2 deductions. That led to 0, 5 being stored in our A register. After 2 more bits have been taken off there, we had this. And of course, as that gets shifted across, that becomes 0A, and then finally 1, 4 on the last cycle after S2 is exited. So at this very last point, we've shifted the last bit of A into R0 here, but it hasn't been shifted into R yet. So it only gets shifted into R on the cycle after we exit S2 and enter S3. That is when the last shift occurs on both R and on A. Okay? This is to get the right values into those registers, and this is a consequence of our improvement of the algorithm. So on our final cycle in S2, we note that the count is 0, therefore we exit and enter state S3. But as we exit, EA and ER are still asserted, and therefore there's one more shift on those 2 that occur when we enter S3. So the final result here is that, let's say 6 in decimal. That's 10 lots of 16, 166, right? And we're dividing that by 8. Well, we'd expect then 20 lots of 8 with a remainder of 6. So 14 is 16 plus 4 is 20, plus a remainder of 6. So that is the correct final result that we see there. But do you note the subtlety that you have to be aware of here in terms of when are the last shifts going to be occurring? There is a very precise relationship between the ASM chart and what we have to code. You have to put all your effort into making sure that the ASM chart is correct and that it reflects accurately what you want the algorithm to do. Because if you code up the ASM chart precisely as it's given to you, then you're going to get behavior that reflects what the ASM chart says, and unless you're completely aware and convinced that that's the right behavior, it's going to be wrong. Hence the questions. When is the first shift done? When is the last shift done? Are these the correct places to perform those shifts? Right, that's a lot to take in. Are there any questions? Shall we just have a break and let it percolate for a moment? Okay. So I'm here. If you've got questions, let me know. We'll start again in 5 minutes' time. previous version of the algorithm.
Yeah, on the previous version, is that because it like reads like C is 0, latches it and then decrements? Or I don't believe in just going that.
It was just the way the ASM charts specified, more than anything else. It's a shortcoming of the ASM design that we're saying here, this is a more action that we want to decrement C, and that means even when it's 0, it's going to be decremented when we enter state 4.
Okay, but it still knows, it still reads C is 0 because...
Yes, C is 0, so what causes the machine to enter state 4 is the fact that C is 0.
Yeah.
It doesn't really matter that C becomes negative, because it's not relied on any further.
Okay, gotcha.
Does both happen in the same clock cycle?
But I mean, that happens in your C code as well, you know. When your for loop exits, you've actually exceeded the boundary, right? So, go on.
Oh, I was thinking because they happen simultaneously in the same clock cycle. So, like the C being decremented from 0 to -1. Is that
Happens at the same clock cycle that we enter state 4. Yes. Yeah. But also, if it happens to be that we can do this subtraction on that last clock cycle when C is 0, that also isn't going to happen until the clock edge that takes us into state 4. It's going to happen in state 4, not in state 3. Right? Because all we're doing is enabling
at the very
the
start?
control signals. But those events don't take place until you have a clock edge as well. And that clock edge happens to take us into state 4. All right, are there any questions about the simulation, about the design? All right. So, if you're feeling a little overwhelmed by it all, I'm not surprised. Don't worry about it. When you read over it, I'm sure it'll be a little bit clearer as well. This final example is nice because it includes the division operation as one of its states. And so we can see here how that entire design gets instantiated within this larger design that involves the accumulation of k numbers and then the division by k to find out what the mean value of those numbers is. All right? So the pseudocode for this is fairly straightforward. We're assuming that a bunch of k registers has been loaded with values. They get accumulated in this first for loop here, and then we perform the division by k in order to determine what the mean value is. So up the top here, we clear the sum, establish how many numbers it is that we're going to be accumulating. The user's going to load some registers up, those K registers up with values, and then we're going to launch into this for loop where we're accumulating the values. So that happens here until the counter has reached 0. And when it does, then we're going to hand over to our divider circuit to perform the division. And when it's done, then we're going to control when the user releases or we're going to allow the user to read the result of the division and then handshake us over to reinitialize our design. Okay, so this is the ASM chart I just talked about. So what's needs to be described is over here. This is a little complicated design. The top half effectively contains our K registers. In this case, K is 4, so it's a relatively small number. And this circuit up the top is really just an address decoder that the user uses in order to enable one of these registers to load the value that it places on data. So that's really just part of the code that, or the design that the user needs to use in order to preload these registers with values. So assuming they've been preloaded with values, we then the start signal is asserted and we perform our accumulation of the value. And the way that's done is by having loaded this down counter with K-1, we use the down counter value to select which one of these register values is added to the existing sum in this cycle down here, where we see the current sum register having a new register value added to it, and that new sum being stored back into the sum register. Once this sum has been determined, those values then get handed over to the divider circuit, which we looked at earlier today, before the break. So the sum becomes the A value that gets loaded into this divider circuit, so the dividend. K, the number of registers that we added together, is the B value, the divisor value. And this circuit will assert the LA and the EB signals to load those values into the divider circuit, and then assert the div signal in order to provide the start signal for our divider circuit down here. It'll then wait for the divider to finish by raising its done flag, which internally this circuit uses the label ZZ to denote when the divider is finished. And then the user can read the remainder and the quotient directly from our circuit. Okay? So there's a little bit of complexity there in terms of how the registers are arranged and loaded with values, but this is really more conceptual. The main part of the circuitry that we're interested in is this part down here. And so the refinement on the, and I have to apologize for the poor projector. I did try to get it changed, but apparently we can't afford to change a projector in the room. Maybe you should, each of you, write a letter to the Vice Chancellor and complain about the fact that you pay $5 grand for a course and don't get a proper projector in your room. I would appreciate it. So in our first state, we load our counter and clear the sum register over here so that we're ready to accumulate the values of these registers. When the user asserts S to indicate that the registers are all loaded with values, we then go into our for loop where we accumulate the values that are contained within these registers. In that case, we want to have the current sum being forwarded through this mux into the sum register. So hence SL is set to 1, and we want to assert ES to reload that sum register every clock cycle until the counter is 0, right? That's given by this signal over here. And while we're counting down, we're going to decrement the counter by asserting the EC signal. By the end of this process, when the Z flag has been raised, when that signal is active, we'll be reading register 0's contents and adding that to the sum given by 1 through k minus 1 register contents. So it'll be the 0th register value that's being added in over here. So as we enter state 3, the very last sum is being written into that sum register. And given that we now have a sum, our circuit can assert LA and EB, which are the control signals on our divider circuit down here, right? We want to assert LA and EB to load the sum and the K divisor value. In the next clock cycle after that, we can then assert the div signal to indicate to the divider circuit that we're ready to do the division. And then we simply wait until the divider circuit is done. Divider circuit will raise ZZ when it is done. And that indicates to us then that the division has been done and the quotient and remainder are available. And then we can assert a done signal to the user so that the user can read that quotient and remainder, and having done so, deassert the start signal S. All right. So rather than go through the details of the code, I don't go through the details of the code. I don't think it's really necessary. We've done enough of going through details of code. I thought a schematic diagram would be useful to have a look at. In this case, the role of the registers that we saw up here and the decoder up the top to be able to address those registers is replaced by a block RAM. Now, block RAM is a resource that's available within our FPGAs. It's simply a block of RAM bits. The standard size is sort of 16 kilobits for one block RAM, or 32 for a double block RAM. So it's really just a big block of memory with an address, a write enable usually, a clock obviously, and we can read some data out of this. What's nice about these block RAMs is that we can change the aspect ratio of the address and the data. So in effect, we have in here, just trying to think how that, yes, 4096 by 18 bits. That's how much data is in one of these block RAMs. But we can change the aspect ratio, so it's 18 bits because that provides us with 1 extra bit per byte, which we can use as a parity bit to check that the contents are correct. We can set the aspect ratio, the width of the data that comes out of here can be anything between 0 and 36 bits. Well, not anything, 0 to 36, sorry, not 0, that doesn't make sense either, 1 to 36 bits. So the data width can be 1 bit, 2 bits, 4 bits, 8 bits, 9 bits, 16, 18, all the way up to 36. Yeah, because that's 18, a multiple of 18, right? So that's really nice. Anyway, suffice to say, up here, in this block that we have up here, this is assumed to be one of these block RAMs, And the way that this block RAM is loaded via data, a write enable signal, and specifically what address we're writing to, that's not actually given in this schematic. What's given in this schematic is the code for our for our divider, for our average circuit. So we have a counter here that will allow us to read every entry of this block RAM, although in this particular case we only have a 4-bit count, and so at most the address can be 15, so 15 data 0. We can read the values that are in that block RAM and then accumulate those in our sum register, which is given over here. So this mux here plays the role of our sum select register that we had over here. So when it's set to 0, then you're loading ground value into this register and therefore a 0 into this register. And when it's set to 1, we're adding to the current contents of the sum register the next block RAM register that we're reading, or block RAM address that we're reading via this adder over here. This is our control circuit. All of the control signals are as have been described in the previous design. So our EC, LC, ES, XL, div, EB and LA signals are all provided by this controller over here. So when we get a start signal, when we have a reset, the LC signal would be asserted on our counter to load K-1 into that. EC is going to be asserted in state 2 while S has been asserted. Here's our Z that's being formed by checking what the output is of this counter. So that tells us that we've accumulated all of the addresses that we have stored away in our RAM. And then finally, after we've accumulated those by setting SL and ES here, the enable on our sum register, then we can assert the LA and the EB signals on a divider circuit that we described previously. And finally, to start that divider off, we have this div signal that is wired to the S start signal of our divider. The done on the divider comes back into our controller here via ZZ, as we saw, and when that gets asserted, we would assert the done signal to the user. Right, so it's pretty much just the design that we've been talking about, but in schematic form rather than in block level form. So let's have a look at a quick simulation of this. So this simulation assumes we're using block RAM, and it assumes that we've loaded the 16 lowest addresses in the block RAM with the numbers 0 through 15, as is indicated here by this value. And we can check that by seeing that as we're accumulating the sum here in state 2, we're getting down to 72 plus 3 is 75, plus 2 is 77, plus 1 is 78, plus 0 is 78. So they're the last values that we're accumulating. Here's the count value as it decreases as well. When the count gets to 0, of course, we want to finalize our accumulation. That's state 3. In this state, we're going to assert LA and EB, right, for our div circuit. How do we know that's happened? Well, we can see that at the end of that cycle, that the 78 that we've accumulated has been loaded here into the Q register, right, at the start of state 4. Our R register is 0 at that point in time. In S4, div is asserted, so the start signal has been asserted for the divider. So the first clock cycle in which the divider sees that start signal is here. So the numerical, well, the counter within the divider is going to be 7 here, 6, 5, 4, 3, 2, 1, 0, and 0 again over here, right? So it starts off with 7, 8 in the Q shift register. And of course, now we're going to be shifting those bits to the left, coming out. And it's only when we see, since there's 16 numbers here, it's only when we see an R value of 16 or greater that we can do a deduction. So let's just do a quick check on that. We have 7, 8 inside our A register, right? So only when we've shifted this guy as well, that's when we're going to be able to do our first deduction, right? So when we see F inside the R register and 0 in the R0 register, can we actually do our first deduction? So here we see F in the R register, so that's where the first deduction can be done. When we deduct 16 from, well, effectively, this is going to be 15 times 2, it's 30. So 16 from 30 leaves us with 14, right? So we would expect to see E being written back into the R register, which is what we see here, right? And we see the 1 that's been put into our Q register at that point. Now, if we have E in the R register, E is 14, right? But together with the R0 register being 0, that's twice 14, so that's 28. So we can again do a deduction of 16 from 28, leaving us with 12, right? And 12 is C. So we see C being written back here into the R register. And when we have C in the R register together with R0, that's 24 less 16, we get an 8 written back into the R register, which is what we see in the very last cycle over here. So this is where we've changed from, this is our very last S2 cycle within the divider. So now we're in S3 in the divider. So the divider has actually already asserted its div signal at the beginning of this, right? So and that's what we see over here. He's asserted his div, his done signal, and it's only the next clock cycle that we can assert our done signal, which is what we see happening over here. So the 78 that we got loaded with here, the sum of the numbers 0 through 15, divided by 16, of course, is an average of 7 with a remainder of 8. So it's a nice simulation, but it requires you to keep thinking about what's going on, and it's not easy to interpret. Are there any questions about it? Who followed it? Okay. Bit of revision then. Okay, and that's it. I don't have more to talk about, and I think I've overloaded you already. I've filled you up with about as much as I can fill you today, I think. Are there any questions about anything? So on Friday, we'll have a Q&A session as usual, but I will also launch into a final lecture on implementation technology. It's mainly a talk about low-level device physics, so if that's not your thing, then feel free to skip it, because it's not examinable, but I felt that it's a nice way of explaining what's below the gate level abstraction that we've used as the foundation within this course. So how are gates actually fabricated and how they implemented using transistors, right? But I didn't think that that's relevant to how you do computations, so we leave it right to the very end of the course, all right? Any questions? Okay, so I'll see you on Friday. But you don't want to ask it in front of everybody else?
No, it's from the exercise.
Right.
So for this one, design a 3-bit counter
Yeah, no worries.
that increments by 2 when it gets an input of 1 and then decrement by 1
Okay.
when it gets
So
0.
this was in my solutions last week.
Yep.
Yep.
In your solution, you after it got to 7, it like the
Wraps
state
around.
8 and 9 doesn't exist.
No,
It
it
just
goes to 0 and 1.
But
yeah.
shouldn't it get to 8 and 9 first, then the next clock cycle it will go to 0 and 1?
What?
Because it said does if present state is 8 or 9.
Well, it's just explaining that in terms of the previous statement, wrapping around if the count reaches 8 or 9.
Oh.
So you just have to read it in terms of that. So there is no state where it is 8. But you can think of, given it's a cyclic number system, 8 is the same as 0.
Yeah.
9 is the same as 1.
Yep.
Minus 1 is the same as 7, right?
Gotcha. Yep.
So that's the intention.
Yep. Thank you.
All right, no worries. See ya.
Thank you.
How do you find the lectures? Is that too long, too much to take in?